So I accidentally turned off that one, so pay attention to this one until it turns back on. Sorry about that. So we started talking about predicting if a reaction is going to, or if a compound is going to dissolve or not. And we looked at our precipitation rules. So we can predict whether something is going to dissolve or not. Now again, that dissolving is not actually a chemical reaction. It is a physical process. We're changing the physical state. But if we take two solutions and we mix them, if we react and form a product that is a solid, so not soluble, we will actually get a chemical reaction. So we call those precipitation reactions. Reactions where we mix two salts that are dissolved in solution and something precipitates out, forms a solid. So we call the insoluble product a precipitate. So for example, if we were to react Ki with PbNO3, we would actually form a solid lead iodide. And KNO3 would still be in the aqueous solution. So we can then filter off the solid and we would get a product. So that's an example of precipitation reaction, and this just shows a nice picture, and you can see the solid forming, so it's not part of the solution anymore. So we're going to look at process for predicting our products of a precipitation reaction. And you'll be doing a lot of these in your general chemistry lab. So first we need to do is take our starting material and determine what ions are in solution. That's our first step, and we've already looked at that. Then we're going to determine our possible products, and typically these undergo by an ion exchange. Remember, if our compounds are already soluble in the solution, then reforming that same compound is not going to be soluble. So what we'll do is we will switch the cations and the anions. Now remember, positive and negative charges attract, so our two anions will not come together. Our two cations will not come together. A cation and an anion are attracted. Like charges repel. So remember that basic concept. Then we're going to balance the charges to get the formula for each product. Fairly straightforward. Now we have to determine, are these possible products, do they form a precipitate? If they don't form precipitate, then they're not going to form a product, because they're still just going to be ions floating around in solution. So if a possible product is insoluble or slightly soluble, it'll precipitate, and that'll be our product in our reaction. If neither product precipitates, we'll just write no reaction, because we won't actually get a chemical reaction occur. If either product is insoluble, then we'll write a solid after the product, and everything else that is soluble we're still going to keep with aqueous. So that's fairly straightforward. And then of course the last step, we're going to balance the equation, because we always want to make sure our equation is balanced. So let's look at one. So here we want to write the precipitation reaction between potassium carbonate and nickel chloride. And this is just our solubility rules, well, the ones that pertain to this product here for us to look at, which of course you're going to need. So our first step, write our formulas of our reactants, because they're given to us in the name. So we need to know what that looks like. So what we have is potassium carbonate. K is in. We have periodic tables to put in this room. I'm so excited. I'll be able to point to it. I don't know when they're going to be up, but they should be up soon. So potassium is in that first row, and our CO3 2-, so it's K2CO3, and of course that's soluble, so that would be aqueous. And then our nickel chloride is in ICl2, because we know it's nickel 2, it's specified to us in the name. So now we want to write those ions. So all I'm doing is breaking up the ions present. And to determine my possible products, I'm going to switch my potassium ion to now be with chlorine, and my nickel ion to now be with CO3 2-. Because again, ions, our cations and anions are going to be attracted to each other. And you can put them into parentheses. That makes it a little bit easier to see that you exchanged them. So now that we've done that, we're going to reform our starting material. Nothing changes on this end. So we just broke it up into ions. We can easily do this step, which was switch them. But of course, this is still going to be these things. That won't change in our reactant. So we're going to write our products by crossing our charges. KCl is balanced. NiCO3. We have 2 plus, 2 minus. So there we go. Now that doesn't mean that these are our products, because our last step is we're only going to get products if at least one of these precipitates. If neither of them precipitate of our products, then we're not going to get a reaction. So our last step is to see if we will get a precipitate to form. So that's when we're looking at our solubility. KCl, we have potassium. It doesn't have any, it's soluble with everything, so we don't have any exceptions, so it's soluble. But NiCO3, that is going to be insoluble based on our solubility rules. So therefore, we will form a product. So since we do form a product, we don't have to worry about writing the reaction. So we just rewrite this. We have aqueous because these two things dissolve. KCl is soluble, so it's aqueous, but this is a solid, so we have to put solid. And if we don't put that change in state, and then it's not a complete reaction equation. Our last step, of course, is to balance our reaction equation. We see we're not balanced. We have Cl2 here, but only Cl. We have K2 here, but only K. So our last step is to balance that equation. Our final equation is always going to be a balanced equation. Now, you do not have to balance your equation if you don't get a reaction, because there's nothing to balance. So if you don't get a soluble compound, then your reaction is just no reaction, and you're done. So let's look at another example. Here we're given, not the names, but we're given the compound, so that makes it slightly easier. So writing down our ions will help us with exchanging the ions. So this step just helps us do that. So we're going to exchange sodium cation with our chlorine to form sodium chloride, and our sulfur anion with our calcium cation. Remember, we always write our cation first in our chemical equation for ionic compounds. So now we're just going to write that as a compound, look at our solubility rules, and determine if it is soluble. So we have NaCl, we know salt is soluble. You can look at your solubility rules, but I mean, it's just table salt. So we know that one's soluble. So we have to look at calcium sulfide. So we have S2 negative, and it's generally insoluble, but our exception is for calcium. So we actually form 2 aqueous, so it's going to be no reaction. We don't have to worry about balancing because there's nothing to balance. We just have a mixture of sodium ions, calcium ions, chlorine ions, and sulfur ions. So we didn't get an exchange to occur. Now we can use this in calculations for quantitative reactions. So here's an example of that. If we want to know the maximum number of grams of PbI2 precipitated, that already tells you we're getting a precipitate, so that's nice. Upon mixing a certain amount of Ki and a certain amount of PbNO3, we can do that. And again, we have our concentrations, we have our molarity, and we have our volume. So the first step in this is you want to draw your reaction, because you need that relationship between your Ki and your PbNO3 and your product to determine your limiting reagent. You can't determine your limiting reagent if you don't know your reaction stoichiometry. Can't figure out your reaction stoichiometry until you write your balanced equation. So that's our first step. So the first step is exactly what we were just going through. We'll take our reactions, our starting material, and break them up into ions. Here we go here. And remember, I'm going to upload all this, so if you can't write what I'm saying really quickly, that's fine. This will be uploaded later on. So make sure you're just following along with what I'm doing, because this will be on Moodle. So we have our ions. Now we can exchange our ions. Potassium is going to now be exchanged with NO3 minus and lead with iodine. And then we're just going to draw our products. Looking at our solubility rules, we see KNO3 is soluble, but clearly PBI2 is insoluble. The equation tells us, our question tells us that. So that's pretty helpful. So, since it's soluble, here is our equation. Our last step is to balance it. So in this case, we have to balance our equation, to balance our NO3. That's really what's not balanced. So again, make sure you can balance equations. So this balanced equation gives us our relationship between our product that we're interested in, PBI2, and our two starting materials. So this is important when we're figuring out our limiting reagent. So now that we have our equation, we can do what we did before to figure out our limiting reagent. And we don't know which one's limiting, but we can calculate that because we know the volume of each starting material we mixed, and we know the concentration. So we can figure out the moles of each of our starting material, and then calculate that to moles of product. So here's our reaction. To figure out if Ki is limiting, we know we have 25 milliliters. Now we have to convert that to liters because our concentration is in moles per liter. That's our molarity. So we have to convert that to liters to do that conversion. Then we can use our concentration. We are told that we have a 0.150 molar solution of Ki. So that means we have 0.150 moles of Ki for every 1 liter. We don't have 1 liter, we only have 25 milliliters. So we can figure out exactly how many moles of Ki that we had in that volume. Once we figure that out, then we're going to use our relationship with our periodic table, our equation, that it takes 2 moles of Ki to form 1 mole of PBI2. So we need that relationship, and that tells us our moles of PBI2. And here I'm showing it converting all the way to grams. Eventually we're going to need that, but that's not really necessary. And we're going to do the same thing with our other reactant. Here we only have 15 milliliters of a 0.175 molar solution. So again, we got to convert that to liters because our molarity is in moles per liter. But we don't have a full liter. We only have 15 milliliters. So that means we don't actually have a whole 0.175 moles. We have less than that. Then our relationship with our equation tells this is 1 mole to 1 mole of our product. So we do that. Even though it doesn't change the number, I want you to always do that part so you don't forget to do it when it matters, because it does matter. So always draw that part, even if it doesn't change the numbers, because it was very important here. Your number would be twice as big if you didn't do this step. This step is very important. So still show it. So what we see is our limiting reagent is our Ki. And if you didn't do this step, then you would predict twice as much, and that would not be your limiting reagent. That step is very important. So our limiting reagent is Ki, and this is our maximum amount of grams that we can form as our theoretical yield. So in this case, we just did everything we've done before, but we had to figure out the reaction first, because you cannot do this without knowing your equation. Why didn't you start? So next thing we're going to talk about is our net ionic equation. So what's the net ionic equation, and why do we care? So equations that describe this, what we just did, that's our molecular equation. signifies everything dissolved in water plus what's a solid. If we actually draw this out with ions, where it's all balanced, we call this our complete ionic equation. But there's something to notice with the complete ionic equation, and that's that there are some ions that are in both sides of the reaction arrow because they're not participating in the reaction. So remember, our aqueous strong electrolytes are written as soluble salts, strong acids, and strong bases. But our insoluble substances are written as solid, liquid, or gas. At this point, we haven't talked about liquids or gases, but clearly we'll use a different definition as an L and a G when we come to that. But right now we have a solid. Because it's not dissolved, it's not an ion. So we have a reaction that has occurred. But also notice that we do have some ions that are in both sides of the reaction. So the ions that are in both sides of the reaction, we call those spectator ions because they're not actually participating, those two words are too similar, in the chemical reactions. They are just hanging out in solution, but not doing anything. So they're just watching. So in this case, we have K plus on both sides of the reaction arrow and NO3 minus on both sides of the reaction arrow. And those are not actually doing anything in the reaction. So they're not part of what we call our net ionic equation, the actual ions that are reacting to form products. So in an ionic equation where the spectator ions are removed, and we're only showing the ions that actually form the precipitate, is our net ionic equation. So in this case, our net ionic equation would be 2 hydroxide ion plus magnesium ion forms magnesium hydroxide. That's our net ionic equation. The other ions are just spectator ions, or what we like to call counter ions. They balance charge, but they're not participating in the reaction. So when we write our net ionic equation, well, first off, if you're not given the products, you have to do the whole thing that we did before, where follow our products, balance our equation, do all that. Here, the reaction is given to us completed, but if I only gave you K2SO4 and 2AgSO3, you should be able to get to this step. We just went through that. Now, to write the net ionic equation of those two things, we're going to separate everything into ions that's aqueous, but we do not separate the thing that is not dissolved. So if it has a solid, liquid, or a gas by it, we do not separate that into ions because it's not ions, it's not dissolved in our aqueous solution. So we're only separating into ions the equations that have aqueous by it. So only those. So we can form K plus, and we have 2 of those, so we just put a 2 in front of it. See, we have K2, so we put a 2. We have 1 SO4 minus ion. We have 2 silver and 2 NO3 because 2 times 1 is 2. Here we form 2 K plus and 2 NO3. Plus we leave this as a solid because it's a solid and it's not an ion in solution. So if it's not aqueous, doesn't have that AQ behind it, it's not an ion. Then we're just going to see what's on both sides of our equation, and we're going to cancel that out. So we have, and I have it color-coded for you to see very clearly, we have our 2K plus on both sides and our 2NO3 on both sides. Now we don't have our SO4 2 minus ion on both sides because that participated in the reaction. So then to write our net ionic equation, we can just write our 2Ag plus aqueous, because it's still aqueous, plus our SO4 2 minus aqueous, forms our Ag2SO4 solid. Our last step is just to make sure it's balanced. It should be if you put the coefficients at each step, but you can always double check to make sure it's balanced, because it should be balanced. So as long as you did that throughout, you shouldn't have a problem, but always double check at the end. So this is our full molecular equation. This is our complete ionic equation, and this is our net ionic equation. And they're all useful for different reasons. when we're describing chemistry. So they're all useful equations to understand the differences of. Let's look at another example. We're going to go through the same steps. Again, the products are given to us. Here, this is not a product that you would, at this point, predict because we haven't talked about gas-forming reactions, but we will in a couple of slides. So at this point, I gave you the products. So we're going to separate Na plus and our CO32 minus, and those are both dissolved because that's where the aqueous meets. And then our H plus and Cl minus. And then our Na and Cl. But CO2 is a gas, so it is not dissolved, so we do not bring that up. And H2O is a liquid. Now, it still might be soluble in water, but it's not soluble as an ion. So we do not break it up. So when you have liquid, that means that it does not dissolve as an aqueous ion. So even though you might be able to see the difference between H2O that's formed and your original H2O that was your solvent, it's still formed in the reaction, so we still can't break it up in our equation. So even though we can't physically ourselves tell the difference, if we were to measure how much water was in our first two solutions we mixed, we would see we're forming more water at the end, if we had a way to measure that. So just keep that in mind. This is additional water, not our solvent water. So here is our full ionic equation, and then again, what we'll do is remove our spectator ions. That's our ions that are in both sides of the arrow. And I have them color-coded for you, so they're pretty clear. Then writing our net ionic equation, and then always double-check that it is in fact balanced. In this case, it is, but you always want to double-check because everything should be balanced. All your ions are balanced here, so if you're continuing doing that, you shouldn't have a problem. But you could always double-check. So for this one, the answer is actually C, and the reason why is because MgCl2 is soluble. It is aqueous. It's not a solid. So you do need to know your solubility rules to do this when you're predicting your products. So BaSO4 is insoluble, but MgCl2 is dissolved, so that means it forms ions. So this is wrong. This is our wrong full ionic equation because this should be broken up and this should say aqueous. So you need to know your solubility rules. Another type of reaction that's similar to our ionic reactions, but slightly different, is our neutralization reactions. Now, we talked a little bit about a neutralization reaction. We did an example where we were trying to figure out our molarity of a base by using a neutralization reaction, which is common. So a neutralization reaction is just when an acid and a base react to form H2O and whatever our salt would be, depending on what acid and what base we start with. So it neutralizes the acid, it neutralizes the base. And at the end of a neutralization reaction, we should have a pH of 7. So it's a neutral reaction. So that's just where it comes from. So that happens when we have an aqueous acid and an aqueous base that reacts to form a salt and water. Not a salt, a salt. So our net ionic equation for a neutralization reaction is always H plus, aqueous plus OH minus. Aqueous gives us H2O liquid. So if it's an actual acid-base reaction, this will always be your net ionic equation. As long as the salt that forms is in fact soluble in water. If the salt that forms is insoluble, then you'll have a slightly different thing. But most cases your salt will be soluble because a lot of the bases you'll see that'll occur. So just keep that in mind. Now again, H2O, that's additional H2O on top of the water that was already our solvent, so we do keep it in the reaction. Even though we can't physically look at it and say, well, that H2O came from our reaction and that H2O was from our solvent. You actually can do that if your solvent is all deuterated water, so OD2 instead of H2O. Deuterium is just a different isotope. So there has been experiments done with that, where we use different isotopes to see the difference. But that's not typical in a normal reaction. So acids ionize in water to form H plus ions. And we looked at that slightly. More precisely, when you talk about acids and bases in Chemistry 106, you're going to be looking at this in more detail. We're not really focusing on acids and bases too much in this particular part of general chemistry. But more precisely, what we're going to form is our hydronium ion H3O+. But most chemists will use H plus and H3O plus interchangeably. So that just happens because water will typically take the H plus to form oxygen with 3 bonds to hydrogen. So 3 hydrogen atoms. For here, we're mostly going to be using H plus, but when you get into this section in General Chemistry 106, you're going to be looking at this in more detail. Now, bases dissociate in water to form OH ions. Bases, like NH3 that do not contain OH ions, produce OH ions by removing hydrogen from water molecules. So that's pretty much our H2O. If we remove one of the hydrogens, we'll form OH ions. So there are bases that do that. In the reaction of an acid and a base, the H plus from the acid combines with OH minus from the base to form water, H2O. So that's our general net ionic equation. So our cations from the base combine with our anions from the acid to form our salt. And typically this salt will be soluble. This is just an example. If we mix HCl and sodium hydroxide, we'll form NaCl salt, which will still be soluble, when we'll also form H2O liquid. And that's where our reaction is occurring. So these are just some common acids. These are our strong acids, and you need to know that those are strong acids. Hydrochloric acid, sulfuric acid, H2SO4, nitric acid, and perchloric acid. Remember how we name our acids? That's very important because we have sulfuric acid as H2SO4. We don't use the hydro when we have a polyatomic ion. So notice that with our naming. So this is just some common acids, but these are our strong acids. So these completely dissociate in water to form our H plus ion and whatever our anion is. The other acids do not completely dissociate, they're in equilibrium. And again, you'll look more at that later on in 106. So we're not going to be really focusing on those things right now. Right now we're just talking about the general reaction. Here are some common bases. Here's our strong bases. Notice your ammonium hydroxide, NH4OH, can be formed from ammonium liquid when it's mixed with water. So you still have that OH, but that's because of water. But pretty much all of these bases have hydroxide in it, as you can see. Sodium hydroxide, potassium hydroxide, and calcium hydroxide are all strong bases, meaning they completely dissociate. The weaker ones don't completely dissociate in water, so they're at equilibrium. For example, baking soda or sodium bicarbonate, which is our chemistry name, but you might know it as baking soda. So we use these in all kinds of things, like lye. You'll see in a lot of cleaning supplies and drain cleaners, things like that. So let's look at an example. In this example, we are writing the aqueous, well, the molecular equation as our full equation, our ionic equation as our full ionic equation, and our net ionic equation, which should be H plus OH minus gives us water. That should be it. So because we're doing an acid-base reaction, we're using aqueous nitric acid and aqueous calcium hydroxide. So we learned how to name these things, so that's our first step to write our formulas. So remember, nitric acid, we're using that NO3, and we wanted balance. And then our calcium hydroxide, calcium is in group 2, OH minus is -1, so we have to have CaOH2. Calcium's in that second column. So now we're going to do just like we did before with our other examples. We're going to write the ions and exchange them. So we're going to form H plus and OH minus, that's H2O water. And that's going to be a liquid. As soon as you see H2O, that's a liquid. And remember, that's a molecule. So that's why it doesn't form ions. And then NO3 minus and Ca2 plus are going to now come together because that's our salts. Then we're going to rewrite this because nothing changed on that part. And we are going to make sure that this is balanced. We have a 2 plus and a 1 minus, so we'll exchange those ions to make CaNO3 2. Our last step for writing this is to determine solubility. It's soluble, and of course H2O is a liquid, so you're going to put an L by it. And drawing that. Now we need to balance it, and that'll give us our full molecular equation. Sorry. So now it's balanced, and I know I'm not going through the balancing every step. At this point, you should know it, so if you're still having trouble balancing equations, please come see me, because that's something that now I'm not going to be doing every time. So you should be able to balance this equation on your own. So here's our balance equation. This is the answer for our molecular equation. Now that we have our molecular equation, we can write our ionic equation. And we're just going to write our ions, but remember, we cannot anymore break up H2O because it's in liquid form. It's a molecule. It has covalent bonds, not ionic bonds. So now we're going to remove any ions that are in both sides of the equations, eliminating, this is our full ionic equation. And it should still be balanced, and you can go ahead and make sure that all the atoms are balanced on both sides. Once we remove that, we'll get our net ionic equation. This is what it should be. Now notice this isn't our lowest whole number ratio, so our actual net ionic equation is H plus aqueous plus OH minus aqueous gives us H2O liquid. That's true for all acid-base reactions where the salts are soluble. So that's pretty much going to always be your net ionic equation, as long as it's a neutralization reaction. Once we know how to do this, we can then apply, just like we did before, to an example. So we did a neutralization reaction before. We talked about it. But here we're not given our products. So for this example, the difference is we don't have our products given to us. So our first step to figure this out is to actually write our balanced equation. So what we have is H2SO4 plus sodium hydroxide. So the first step is we have to write our actual reaction. So exchanging our ions, we get, of course, water, because it's an acid-base equation. And we have to balance that. So we have SO4 2 minus and an Na2 and Na plus. So that's Na2SO4. And then our last step, forgot aqueous, is to balance our overall equation, because we need that balance equation to then do the rest of this question, which is figuring out our concentration of H2SO4 that we need if we're using 35 milliliters of 0.150 molar NaOH. So we need to have that relationship in our chemical equation. Yeah, I know, we're getting there. So our last step before we can actually answer this is to balance our equation. No, it's okay, but we're getting there. So, don't say that out loud.
No, I'm saying it, that's why.
So when we balance this equation, we see that we now have our stoichiometric ratio. So now the question is asking, we know how much volume of H2SO4 we have, and we neutralized it with sodium hydroxide. It took 35 milliliters of a certain concentration of sodium hydroxide. So what we're trying to figure out is what was the original concentration of H2SO4. So what we need to know is how many moles of sodium hydroxide did it take to neutralize our H2SO4, and how many moles of H2SO4 did we have. So we can do that because we know, based on our chemical equation, that for every 1 mole of H2SO4 reacts with 2 moles of sodium hydroxide. So since we know that relationship, we can do this. So we know we have 35 milliliters of sodium hydroxide. What we don't know is how many moles of sodium hydroxide are in here. But we have that relationship in our molarity of sodium hydroxide. That tells us that for every 1 liter, we have 0.150 moles of sodium hydroxide. So we have to convert this to liters. And then we can use our concentration to figure out how many moles of sodium hydroxide we originally have in 35 milliliters, because we don't know, but we have our concentration. So that is 0.150 moles of sodium hydroxide per liter. So now, if we figure out what this number is, that tells us how many moles of sodium hydroxide we have in 35 milliliters. So we know how many moles it took to neutralize our H2SO4. So to figure out how many moles of H2SO4 we have, then we can use our relationship of our chemical equation that tells us that it takes 2 moles of sodium hydroxide to neutralize 1 mole of H2SO4. So that'll tell us how many moles of H2SO4 we have. And again, because of time constraints in space, I'm just putting this as 0.0026, but make sure that you're not rounding too soon. I would really wait to round at the end, but this is just because of space. So that gives me how many moles of H2SO4 I have. I want to know my concentration, but I know how much volume of H2SO4 I have, and my molarity is moles over liter. So I know my volume, but I need my volume in liters. That's milliliter. So I need it in liters. So now I have my volume. Now I have my moles. I can figure out my molarity. And this is exactly like the example I showed last time. The only difference was we had to figure out the chemical equation first. So that gives us a 0.105 molarity. So you can do this, and we're really building up on what we've been doing. Again, this will be up on Moodle, so you'll be able to go back and make sure you can work on that. Sorry. I don't know why it does that, and it drives me crazy. So let's look at the next thing. Like I said, we haven't talked about a gas evolution equation, so now we're going to look at an example of equations that give other things besides solids or our acid-base reactions. But first, let me erase this stupid writing. So some reactions form gas directly from the ion exchange. So for example, this one, if we react potassium sulfide and our sulfuric acid, we actually get a K2SO4 aqueous solution, but we form H2S gas. So other reactions don't directly form gas, but instead they decompose to form a gas. So for example, if we mix K2SO3 and our sulfuric acid, we get this K2SO4 aqueous and H2SO3 aqueous. But in the presence of water, H2SO3 will degrade to form water and SO2 gas. So that is still a gas-producing reaction, and that happens, you can't really stop it. Once you form that H2SO3, it's going to decompose to form water and gas. So how do we know when this happens? Well, we're just going to have to memorize it. Sometimes that's the case. And remember, this is based on experimental note. So if we react sodium bicarbonate and HCl, that is a neutralization reaction. And you've probably all done it, especially in high school or maybe even junior high, where you mix vinegar. This is HCl, but we can do it with vinegar. Vinegar and baking soda, and you put a balloon on top and the balloon blows up. That's because we're forming, in that case, CO2 gas. So that's a gas formation reaction. We often can see the bubbles. Or you might have taken vinegar and baking soda and put it in a little cap. It used to be like a film canister, but I don't know where you find film canisters now because who has film. And then the top pops off. Again, that's because you're forming gas, and we'll be talking about pressure in chapter 5, which hopefully we'll get to on Friday. So here's what you need to know to predict when a gas reaction is going to occur. And you need to know these, and that's just how it is. So if you have a metal in sulfur or a metal in HS, and you react it with an acid, then you're going to form H2S, and that's going to be a gas. Use your regular solubility rules for the salt that forms, but if you form H2S, you're going to form a gas. So this is when you react a metal or HS that has sulfur present and an acid. Because remember, your acid forms H+. If you have a metal in CO3 or a metal in HCO3, and you react it with an acid, then you're going to form H2CO3, which decomposes to form water and CO2 gas. So that would be an example of your baking soda reactor. If you have a metal in SO3 or a metal in HSO3, that one's going to form that H2SO3, and that will decompose to form SO2 gas and water. Notice all of these are reacting with acid because you form that H that switches. The only one that's not reacting with acid is when we have the ammonium ion, NH4, and we react it with the base, we're going to form ammonium hydroxide, and that's going to decompose in water to form NH3 gas and H2O. So that's the only one that you need to know that's reacting with a base. Everything else is when reacting with acid. If it's not reacting with acid, you don't have to worry about the gas formation. So you need to know these, you need to know this table, you need to know what forms. And you need to know the final equation is going to be the decomposition. This is going to be your final equation. So let's look at an example. We have sodium carbonate and nitric acid. So we have an acid, so we should always watch out for this, with the one exception with the base. So our first step is the same. We're going to write our formula, Na2CO3 aqueous and HNO3 aqueous. And then writing our ions, here we go. So we see we have the CO3 2- ion and we have an acid, so we should automatically think gas forming CO2. Remember, that's just carbon dioxide. So we're going to be forming CO2. So we're going to exchange the ions, and we form the Na plus NO3-, that's fine, but we form our H plus CO3 2-. That's going to decompose. So we check, are any of our products H2S? No, of course not. So we're going to check if they decompose. It does. As soon as you see that carbonate, you should think of decomposition. So NaNO3 is soluble. That's fine. And then we're going to draw our decomposition product for CO2 and H2O. So our final product, our final reaction, our full reaction, will not have this. This will automatically decompose. So as soon as you see that, you're writing CO2 and H2O. CO2 is a gas, H2O is a liquid. Now you do still have to use your solubility rules to check for the salt, to see if it's soluble or not. So once we write this, our last step is, of course, to balance the equation. I have it balanced, but that's your last step. If I ask for your net ionic equation, remember, you're not breaking up CO2 and H2O because they are not in the aqueous state. So once we make sure our equation is in fact balanced, that's our full equation. We can write our net ionic equation, and we can write our full ionic equation from that. So you have to recognize those gases, so know that chart. There are some other patterns of reaction. We've talked about precipitation, that's forming a solid. We've talked about an acid-base reaction, that's reacting an acid and a base to neutralize, forming H2O. So our net ionic equation is H plus OH minus forms H2O liquid. And then we just talked about gas evolving. All of those involve exchanging ions. But that's not the only types of reactions we can do. Other reactions actually involve the transfer of electrons. So when we have a transfer of electrons, that's called an oxidation-reduction reaction. Now these precipitation reactions, the acid-base reactions, the gas involving, those already have ions. We're not exchanging electrons. But let's say we have sodium metal and chlorine gas to form our sodium ion and our chlorine ion. That is a transfer of electrons. So those are the reactions that we're talking about next. And they're known as oxidation-reduction reactions, and sometimes it is shortened to redox reaction. So reduction, oxidation, bless you. So you might hear the term oxidation-reduction, or you might hear the term redox. All of organic chemistry is technically, we're looking at transferring electrons, but we don't always describe it in oxidation-reduction terms. Technically, that's often occurring. So we need a net change in oxidation state for us to really call it an oxidation-reduction reaction. So for example, if we take iron solid, our metal, our elemental iron, we react it with O2, we're going to form an ionic compound, Fe2O3. That is involving our metal giving up its electrons to oxygen. So that is a transfer of electrons. So we don't have a transfer of electrons in any of these other reactions we've been talking about. We already have the ions present. So in these cases we do. So combustion is, in fact, a redox reaction. And we've looked at combustion a little bit. We have some sort of compound here. We're showing 2H2 gas. We've seen this with our carbon-containing molecules as well. Reacting with O2 to form, in this case, H2O, and that does involve a transfer of electrons. So that's, of course, combustion of hydrogen gas. Very combustible. If I put hydrogen gas in a balloon and light a flame to it, it'll blow up. It's fun. I don't have any hydrogen gas to do that, though, so sorry. Another example, actually forming ions. If we take two elemental compounds, we react them, sodium metal and chlorine gas to form NaCl, then that is an exchange. Sodium is giving up its 2 electrons. So we'll talk about these equations. This is our electron equation. We have 2 sodium metal elements, and we're forming our ions. To form our sodium ion, 2 electrons have to be given up to something. And chlorine is accepting them. So our equation, our redox equation for chlorine accepting them, is our Cl2 is taking 2 electrons to form our anion. Our cation that forms always gives up electrons. Our anion that forms takes electrons. So this is just representing it in a chemical equation. And we've talked about that exchange before, so now we're representing it. So if we look at these 2 reactions, another reaction is reaction of metals and nonmetals to form those anions. So what we're doing is an exchange of electrons to form those anions. So we're converting it to free elements into ions by transferring electrons. So something has to lose electrons and something has to gain electrons. So that's where we're going with our redox reactions. So a reaction where electrons are transferred from one atom to another, or our redox reactions, atoms that lose electrons are being oxidized. You need to know this terminology. The atom that gains the electrons are being reduced. This is important. Now I'm going to confuse you with some terminology, so you need to know this one first before I go on. So for an example of taking sodium and reacting it with chlorine to form our normal sodium chloride, sodium is giving up an electron, so it's undergoing oxidation. Chlorine is accepting an electron, so it's undergoing reduction. And we can say that chlorine is being reduced and sodium is being oxidized. Now, where does that term oxidized come from? When this was really first noted, a lot of times this was noted with oxygen. For example, iron will oxidize to rust in the presence of molecular oxygen in the air. And also in a lot of organic chemistry, oxidation occurs when carbon has more bonds to oxygen. So that's where that term oxidation comes from, that's why oxygen's in it. But oxygen does not need to be present for an oxidation to occur. Not by the true definition, just a lot of times you will see oxygen. And when it was first really noted and understood, it was understood with oxygen. So that's why you see that term oxy and that oxidation. But oxidation in full definition is just when electrons are lost. So that's oxidized. It doesn't have to contain oxygen, but oftentimes it does. You can remember this mnemonic, oil rig, oxidation is loss, reduction is gain, and it'll help you remember that terminology. If a reaction is not a metal and a non-metal reacting or doesn't involve O2, we do need a better method for determining how electrons are transferred. So chemists assign numbers called oxidation states. And we're going to talk about our oxidation states. I'm going to stop on this slide next. So I want you to start reviewing our rules for oxidation states, because you're going to need to memorize them, because sadly this book doesn't really explain it in a way that makes sense except for memorizing. But oxidation states are non-ionic charges, which is going to be very important. So I want you to start going through those rules and be familiar with them before the next class. Because I'm going to be going fast, so it's best you understand them a little bit. There is a Chem Club meeting tonight, if anyone's interested in the Chem Club. On Moodle, the dates have been up all semester. So that's in 165 at 5 o'clock. And don't forget, we do have a speaker on Thursday.